Thanks everyone for coming to the Skip Ratchet. Depending on when you looked at the schedule, you might be surprised that I'm in fact not Quinn Wilton. Quinn is unfortunately ill, not COVID, but still very serious, and is improving, is very disappointed that she won't be able to come speak, but she's working on a lot of things that I think could be described as strange loop bait, so I'm sure she'll be able to give a talk next year, or maybe in a future session. Quinn, when you see this video, please get well soon. So she reached out last week to see if I could fill in and shared her notes, and so this is the resulting presentation. My name is Brooklyn Zelenka. You can find me on the internet as Xpeed. I am the co-founder and CTO at a company called Fission, where we're working on infrastructure and software for edge and local first software. And my background is not in cryptography. I'm mainly a programming language geek and also have a background in VMs and increasingly distributed systems. And do a bunch of work in various standards as well. And I actually wrote the original Skip Ratchet paper. So I guess it's not entirely, I'm maybe not entirely the wrong person to be the substitute speaker today. So why do we even care about hashes at all? Well, and especially the Skip Ratchet, well, there's a whole bunch of uses for this, right? So as I mentioned, we're doing a lot of stuff with local first software, and that's really an emerging space, right? It's saying, what can we do completely locally and only synchronize when we absolutely need to, right, with other people. And that means that there's a lot of new ways of doing things and low-hanging fruit that nobody's really looked at before. But it also means that if you're working in this space, you have to invent lots of stuff completely from scratch. But you end up finding and going down different paths from previous people because you're in a have different constraints. One of the things we've built is the WebNative File System, which is a distributed private file system that the Skip Ratchet came out of that work. And we were describing a lot of the internals and the key management to some folks at Protocol Labs, who are the people behind IPFS, if you're familiar. And they said, oh, wow, that Skip Ratchet actually looks really useful. We think we'd have some use cases for that. Could you write that up? And we did, and it's actually finding its way into a few places now. There are implementations, public implementations in TypeScript, Rust, and Golang, and at least 2 that are inside of private projects that are in Haskell and Elixir. So aside from just private data, we've also found use cases for it with Electric coins and micropayments and payment channels. So this is both mainly off-chain payments that may or may not settle onto a chain, deterministic wallets and various kinds of key management, and long-running asymmetric channels. So when you have, say, 2 parties that are going to be talking, and one of them is going to do 1 billion writes before the next one comes in, and you need to be able to seek randomly inside those 1 billion messages, this makes those lookups much faster. And as I mentioned, we have a lot of keys in this distributed store because we want to keep everything encrypted at rest. And the core problem that the Skip Ratchet solves for us is we need to, without revealing that there's been a write to a particular file, just that there's new stuff being written, so we've hidden the entire structure, somebody should be able to deterministically look up and find a key for a node that they didn't know existed until they looked it up. And that might be thousands, millions, billions, trillions of writes after the one that they had seen previously. And doing that in linear time obviously is terrible, so this lets you jump to an arbitrary point in logarithmic time. So the talk today is really a tale as old as time as far as strange loop goes. This is a bunch of programming language theorists dabbling in distributed systems and cryptography, finding new ways of thinking about a problem, and hopefully finding something useful. It's a really, really simple idea. It has a couple moving parts in it, but simple means it's relatively easy to get started with and seems to have lots of applications. We keep finding more. And we had an interesting way of arriving at the problem, or at the solution, rather. So I'm going to take you through part of that as well, because it's also a good bootstrap into how the whole thing works. So today we're mainly going to talk about number systems and applied crypto. So to get started with some fundamentals and just sort of level set, a hash chain, or sometimes called a ratchet, is when you take some bit of information, some data, we'll call that a seed, and you hash it to get a random-looking string that's uniquely determined from the inputs. So when you get the hash on a git commit, we took the diff and your commit message, hashed those, and got this random string. But then we can take this string and hash that again and again to get the, the hash of the hash of the hash of the hash. And it's really hard to say that many hashes in a row, so sometimes we use this notation instead, where you have hash raised to some power to mean we're going to do it that many times. And there's two main directions you can go with this. There's actually some other structures as well, but the two main use cases are producing a pseudo-random stream. So this is a random number generator, but cryptographically secure, where you start with some seed. So that could be some pre-agreed secret, or maybe you're going to use something like Diffie-Hellman key exchange to generate a secret on the fly, and you're going to send a bunch of messages. And you want to make sure that everybody agrees that message 1 has a certain key, and message 2 has a different key, and message 3 has a different key, and so on and so forth. And if somebody breaks into message 3, they can't read 1 and 2, though they could then read further messages. Right? Lamport took this idea and reversed it. And so this is the same Lamport from TLA Plus and LaTeX and Paxos. He shows up kind of everywhere. And so we have the same thing. We have a seed, we hash it, we double hash it, we triple hash it, and we get to some distance. So we've made, let's call it 1,000 hashes, and we use that as a commitment. We say, I'm going to use this to authenticate that I know a secret that nobody else does. Right? So this is a very, very light way of authenticating who you are. You then can send that to some verifier who doesn't even know how many hashes there have been necessarily. This is just hash X. And when you want to interact with them, you give them the pre-image, the input that would then hash into this value. You send that across, they can hash it and check, yep, great, that's you, that is hash x minus 1. And we can do this on and on and on. This has a couple of problems, as you can imagine. To get to generate that initial set, it takes n steps. You then either have to store n of these, or generate them on the fly. So there's a space or a time trade-off with a certain size. And you will eventually run out of hashes. You'll get back to that last seed, and then you have to set this whole system up again. And a single person-in-the-middle attack can be pretty devastating to this. If I have those 1,000, and you somehow manage to block messages 500 to 600, and then you get the key for 500, you can now do 100 interactions as me. Right? This is a big problem. And that sounds hypothetical, but this is actually actively practical exploit in the wild. Sami Kamkar has this really great video from, I think, 2015, where he shows reading off of a keyless entry on a car, just pressing the button several times away from the car, recording the responses, and then just walking up to a vehicle and replaying them, and being able to unlock the car. Using something like Lamport OTP, you can build a really simple payment scheme. So we'll say that each of these hashes is correlated to a bank account, and each hash is, just to keep it simple, 1 cent. And I can now use this to do streaming micropayments. So somebody may send me some blocks of a data structure, and I say, OK, great, here's the second hash in that sequence, and then they can go to the bank and say, hey, here's some hashes, give me money. And then we can repeat that process. So obviously, if we have things that are like a hash of a hash of a hash of a hash, this is a little bit like counting, right? Counting by saying 1 and 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 1 isn't really super practical. It definitely works. But there are definitely better ways of doing it that we use on a regular basis. But it turns out we've been counting this way for a really long time. So this is the Ashango bone. It's actually not the oldest one. The oldest is the Lebombo bone. I think I'm saying that right, which is carbon dated to about 44,000 years. And unfortunately, there's no appropriately licensed images of the older one, but it looks roughly the same. And essentially, it's a piece of bone where they've done tick marks into it to do some kind of counting. It's conjectured maybe they were doing some basic mathematics. To put that in perspective, we've only had agriculture for about 11,500 years. So we've been doing at least tick mark style numbers for 4 times longer than we've been growing our own grain. Animals also seem to have some concept of number through tick marks like this. So unary counting, if you've ever done inventory or stock or something like that, you've probably seen a bunch of tick marks like this. 1 tick is 1, 10 ticks is 10. And you can orient the ticks in different ways to kind of help group them. But it doesn't really matter. If I have 5, with a slash through it, and 2, if I put it before or after, it's just the number of ticks on the page. We can make this work as a data type as well. So this is called a piano number. You have 0 or the successor to some other number. So 1 then is successor with 0 in it. And 2 is successor with 0, and so on and so forth. So this is essentially tally marks, but as a data type. We can even take that one step further and use church numerals. This is how to represent purely as functions the number 0, right? So we say we'll take a function and throw it away, and I'll give you back whatever the inner data is. Or if I want to do 1, I'll apply that function once. If I want to do it twice, I'll apply it twice, and so on and so forth. And if I can lay this out differently, you can see how they nest inside of each other. And that's nice and academic, but if we apply a hash function as that function, we now have a hash chain, right? So we now have all these different ways of representing number. The major difference is that in the hash context, you don't know what the number is. You just know that it is at least 3, because that x inside might be the result of a bunch of other hashes. And this is a really important property. It means that we've essentially encrypted the number, or at least the segment that wasn't provided to us previously. Positional numbers it's still just number, right? But we're just putting them next to each other, and there's lots of different ways of representing numbers efficiently this way. The best feature about positional number systems, the ones that we normally write, with numbers in a sequence, is you can just throw a number in front, and you get a bigger number, right? Of course, this has some downsides, right? We need to actually write out on a check, in English, 25 and however many cents. Right? Doesn't work that way on all number systems, even if they're positional. So in Chinese, they use a different character for the hundreds digit or the thousands digit, et cetera, even though they are still positionally oriented. So we've all seen this before, right? You have 0, you have 11, which means you have 1 in the tens in the ones column, and 582, you have 5 hundreds and 8 tens and 1 2. And that works as such because these are all in base 10. But you can take this really far and do things like mixed radix numbers, where each position has a different base. So the 1s here is in base 4, the 4 is in base 12, and the 12's digit is in base 111, right? And so the actual numbers underneath, look different. The representation looks different. But it still represents the same number, right? But it gives us a different way, a different level that we can move how quickly by changing certain numbers, by changing just a single number, rather. That doesn't sound super practical, but we actually use these all the time, right? So in date times, for example, so 2022, September 22nd, right, 11:22 a.m., these are all in very different radices, right? 7 days a week, 52 weeks in a year, 24 hours in a day. We also do this with currency and denominated currency. So yes, the $20 in a $20 bill is equivalent to 20 coins, but if I have physical money in front of me, these are actually in different bases. So let's do that with the hash. As we said before, from church numerals, 0 is just not hashing things. If I want to represent 11, I can hash the 10th digit and the 1's digit once each, And that's on different data, so we get different hashes back. And to do 512, I do 5 times, then 8 times, and then twice, which is really just piping it through a bunch of SHA-256s. So now we can do things like a denominated payword, where we have multiple of these streams and multiple commitments, these largest hashes, that represent 20s, 5s, and 1s. And as we go, we're going to start from only representing or only revealing these furthest ones, and I want to pay a $20 bill. There you go. I've given you that hash, and I can do several of these and one of those. And now we have a really easy way of counting out certain amounts of money rather than having to reveal thousands of hashes potentially. This is also related to data structures because, of course, we want graphs in our crypto. This is a skip list. Well, actually, this one first here is just a linked list. Most people are introduced to skip lists as a probabilistic data structure, but there's also a deterministic version where we say, in this case, we're only going to jump back by 2, and then above by 4, and then again by 2, and above by 4, right? And so this makes it really easy for us to move across the digits much faster, right? To get from H to D, I can do it in 1 hop, or to get from H to C, I can do it now in 2, right? I can do 4 plus 1. This is sometimes represented like so, where you have almost like a fast track above. So all the green nodes are connected directly, and also down to the blue nodes, and so on and so forth. We can now finally talk about a simplified version of a skip ratchet. This number represents 0, and this is going to be specifically a binary skip ratchet. Again, you can make the radices for each of these elements whatever you want, right? To increment it, I leave the larger 2 elements the same, and I hash the smaller element. And then I'm now out of, because we're in binary, I'm out of hashes for the small element. So I hash instead the medium element and derive from that the small element, which gives us the ability to have a jump in the middle, right? I can always increment the medium one without touching anything else and overwrite the small value. We can keep going. So here's 3 and 4. And of course, because now we have that 1 in the highest position on this binary, we've hashed the largest value, which has given us a brand new medium and a brand new small. We can get a jump now from the middle value to the last one. And all of these values can get to the end by incrementing the largest value once. Right? So we can skip right to the end in a single operation from any point in this epoch. So that's like really the basic core idea, but there's actually a fair bit more to go still. We want to generate single things like keys back out of this, but we don't want to give away the internal state. So we can combine the however many levels we have, I'm just going to use 3 because it's easy, into a single value. XOR is completely viable for this. It's very, very fast, just doing a binary XOR. It does have some edge cases where it could leak information, and so using a hash is probably a better option, concatenating them together and then hash. This means that now, if we take from a higher level, we have our seed, we generate from that the first state, and then we can increment through all these different states. We can do jumps between states, and even going to the very end. And out of that, we can generate secrets that have nothing to do with each other. So unlike in, say, a regular hash chain, if I give you a key and that there's going to be further keys to, but I haven't given you the internal state, you cannot discover the next step in this secret chain, right? You get nothing. So we want to introduce a little bit more security into this system. We want to think about each range. So we call these epochs and zeroing. So in our normal number system, here we have 10, 11, 12, et cetera, 18, 19, and then 20, right? So here's my tens range, and inside of that I have 0, 1, et cetera, 8, 9. And this is my tens epoch. Then I have some 20s, and it looks kind of the same, right? Nothing too fabulous there, other than we're going to use this kind of a diagram. To do this on encrypted numbers, we take from the previous epoch, so the 10s, let's say, to get to 20s, you hash that number and derive a new medium value. But we don't want to drive it off of this latest one. We want to drive it off of the previous one, so that even if I give you the entire current state, you can't find the 10s digits. So we use some salt, some randomly generated number that can even be public, doesn't really matter, and we merge that with the previous state, or the previous large element, and then hash that to get the medium. And again, this prevents us from seeing any previous values and limiting from what point in time onwards you can see in this chain. And we can do this with any number of levels. The diagrams start to get pretty hairy as you increase the number of levels and the size of the radices. But so this is just for binary version. And here we have, again, that common salt in pink on the far left. Our seed is at the top left. We hash that to get a large seed, we call it, or you can think of it as like pre-L. We merge that with the salt and hash to get the next pre-M, and merge that with the salt to get the first small value. And then we hash the pre-M and the pre-L to get the initial state. So this is just to get started and just set up. And every time we rotate the large value, we go through this process, except the seed is the last large one. We also want to hide what the number is, so that somebody, they can count and say, oh, well, I know that this only has 10 digits. I can hash 8 until I run out, so this must be 2. And we want to hide that as well. So to get started, we generate these values, and then immediately take a random number and increment it by that. So this is a little bit like moving the 0 in your number line over. And then from this one, we had 5 there, so we generate 4 to get us the pre-image for the medium epoch. Generate from that the small, and then also take a random number there and increment it forward. And then this here is 0, even though it is whatever the large that we're in plus, and then 50 and 42. Now, I said random number. You can literally do this with a random number generator. If you want a totally deterministic scheme, so you have lots of different people generating numbers this way and you'll just share that initial seed, you can use information from the L-1 here, the large pre-image, to maybe take like the last byte, and that will tell you, increment this one by this much and that other one by this much. It's also a mixture of unary and positional numbers. So it's not all positional, because then we would need to keep increasing the number of digits we have. But we only have, in this case, 3. So the top digit acts like tally marks. It's still completely unary, and it's just a stream. It is a regular hash chain. The values inside of that are positional, right? And they're positional based on the unary digit that they're underneath. We can limit ranges as well in here. So here I have a 4-part skip ratchet. It has a small, medium, large, and we'll just call it grand as well. And I'm not going to share with the recipient of this these top 2 values. I'm going to take them and hash them together or XOR them. We can add those together and give you G plus L without revealing G and L. And now you can move forward until you run out of this combined value, which puts in it a limit, a hard stop, on how many numbers you can generate and how many keys you can go for. Then they can come back and say, hey, I need the next tranche, I need the next group. And so you say, oh, great, and you hash the large value, you combine them again, and now they can progress inside of that area. This means that, and so this top one now has changed to G plus L versus the last one. This means that if we have some stream of data, maybe this is a Merkle tree, or maybe this is literally a stream, I can give you access to, by sharing you the first medium value, I can give you access to both of these pictures, and this one, both of those, and this one, both of these. Or if I give you this large combined value, just this range and nothing else. So, to wrap up, this is a simplified picture of a skip ratchet. You have all these different states. You can generate from that secrets. You can hop between them really quickly. And the secrets that you generate out of it aren't correlated to each other. It gives you really fast secrets, thanks to this positional structure. You can never run out of numbers, because the top number is just a unary counting digit. You can go forever. This is in production in a few systems, and we're still finding more uses for it. There's these separate ideas, things like skip lists and counting and positional numbers, that share some common basis that we were able to take and recombine and turn into a hash system. And there's still tons and tons of low-hanging fruit like this out there. If you want to see a system that uses this, that this initially came out of, the WebNative File System, I'm giving a talk about it tomorrow in the next room over, I believe, right before the closing keynote. And if you like diagrams of data structures that kind of make you scared because it looks like category theory, we have lots of those in that presentation. So, thank you.